Welcome to the demo video of caddesignnow.com. In this video, I'm going to tell you how do we design an entire product. And in this course, we are going to learn that any product like this tool, how can it be designed from scratch? Okay, and we are going to use CATIA, we are going to use Hypermesh. This is the interface of Hypermesh, and we are going to use Abacus. And why all these softwares? Because these softwares are used in industries. These softwares are used in IITs and ISC. And I am from ISC Bangalore, and I also worked in Tata Motors R&D in Pune, and believe me, these softwares are used there. This is the geometric model of a stool that was made in CATIA. This can also be made in softwares like AutoCAD or SolidWorks or any other software. Okay, and all CAD softwares are almost the same. All they do is convert your ideas to a product. This is what you do in a CAD software, right? Yes. But what if I tell you that this is not entire design? Because most people believe that this is design. Whatever you make in a CAD software, it's not a design. For example, you made a concept out of your ideas in a CAD package or a software, let's say AutoCAD, and you went on and manufactured it. And when you sold to a customer, let's say when he sits on it, the stool breaks. This is not design, this is disaster. So I'm going to tell you what design is. Design of a product means that, for example, in case of this stool, let's speak of design. The design of a stool means that when a person sits on it, it should not break, right? Will you ever take a stool that breaks when you sit on it? No, it should not break. So this is why CAE is important. This is what we are doing in Hypermesh over here. Okay, this process will become clear to you as we proceed. Okay, now first thing is that firstly you make CAD in any CAD software, as I've told you, and import it in Hypermesh. Why Hypermesh? Because it gives more control to create a finite element model which looks something like this. Okay, as you can see, it looks exactly like the geometric model of stool, and it should actually look exactly like that. Okay, now our design is always based on maximum load that acts on it. And let's say that a 100 kg person is going to sit on it, and the load corresponding to 100 kg person is 1000 newtons, right? M into G. That exactly comes out to be 980 newtons, but let's say, or let's round it up to 1000 newtons. So what I've done, I have applied a concentrated load of 1000 newtons in it, as you can see. Okay, now let us say that this red portion is the cross-sectional area of the person when he sits on it. Okay, he's obviously not going to sit on the entire stool. That could also have been done, but let's assume that this is the contact area. Okay, and I have applied load to all the contact area that you can see, which is represented by red. Okay, now the solver needs some boundary conditions for it. Okay, without boundary conditions, it's difficult for the solver to come at a conclusion or a result. So we have applied some boundary conditions over here. As you can see, few nodes I have constrained. Constraint means that they are not allowed to move in any direction, they are fixed. And I have given the material of this tool as polyethylene terephthalate. Okay, and I have assigned elastic properties of polyethylene terephthalate with modulus of elasticity as 3000 megapascals and Poisson's ratio as 0.4. Okay, so this is the whole finite element model that we develop in Hypermesh. If you are not understanding it right now, you will get it through practice. This is a very easy stuff. Okay, now what I'm going to do, I'm going to export this model. Okay, and I'm going to open Abacus. Now let it open, it will take some time, and let me tell you, this is the standard process that is followed in any industry. If you know Hypermesh, if you know Abacus, you are going to get ahead in time, because this is the future. Let me tell you, if you belong to mechanical, civil, production engineering or aerospace related branches, this is the future of it, and you must be willing to learn this. Now I'm going to export this FE model. FE means finite element. Okay, I'm going to export this finite element model. I say export, and I'm going to open it in Abaqus. So this is the model over here. This is the same file that we had made here in Hypermesh. What we are going to do, we are making a model in Hypermesh and solving that model in Abaqus. This is only because the solver of Abaqus is much better than any other solvers out there. It's much better than ANSYS. That's why we are not using ANSYS here. Okay, so I'm just going to create a new job and I'm going to run it. These softwares are very much useful if you go to any industry, any IIT or ISC, even if you want to do MS from outside, let's say Germany. Yeah, now the job is completed. I'm going to right click on it and click on results. Let me animate it. So this is how the animation comes, and as you can see, and when I zoom in, these are the regions of very high stresses. Okay, and this is what it's telling us. Through these reasons, the material or the stool might break. This is what it's telling. Okay, if it breaks, obviously it's going to happen through these areas or starting from these areas. This is what I'm trying to tell you, because red means maximum stresses. Okay, now how do we say that the material is failing or the product is failing? We just look at the von Mises stresses. Why we are looking at von Mises stresses? Because this is a ductile material. Okay, and the yield strength of this material, polyethylene terephthalate, is 80 megapascal. Let's say we take factor of safety of 2 to be sure about the design. Okay, we say that maximum von Mises stresses when exceeds yield strength upon factor of safety, the material breaks or fails. Okay, here yield strength is 80 megapascals, factor of safety is 2. So if this maximum von Mises stresses is greater than 80 upon 2, which is 40 megapascal, this will break or fail. Okay, and certainly 9.227 is not greater than 40, so this is not failing. Certainly it's not failing because this number 9.227 is lesser than 40 megapascals. This is how we tell if a material is failing or not. Now we say that this design is acceptable, but this is not the final design because we need to optimize it. Okay, this is acceptable, certainly acceptable, but we need to optimize it. Why optimization is required? So that we can cut costs. Okay, so that the company earns profits. This is the sole reason of optimization. Okay, now we go back and let me tell you that this tool had a thickness of 5 mm over here, and right now what I'm going to give is 2.5 mm of thickness. So the first method in which we can optimize a product is by reducing the thickness of it. Okay, reducing the thickness means that we are reducing the material used in the product. So 5 mm was acceptable to us. Now let us check it in 2.5 mm. Okay, so again I'm going to run it with 2.5 mm. All we have to check is the maximum von Mises stresses must not exceed 40 megapascals. This is our sole objective. This is what we'll be doing. Okay, so this is completed. I'm going to visualize it, and as you can see, See, 38 megapascals is the maximum von Mises stresses, which is slightly lesser than 40 megapascals. So here we are going to stop. Okay, here we are going to stop because this is under limits. I hope this is making sense to you. So we say that optimized thickness of this product is 2.5 mm. Okay, now what else can be done to optimize this product? Secondly, you can go ahead and change the material of this. This is very obvious, right? You find some other material of same strength, you can change it. Now the third method that I'm going to share with you is to remove the materials. What I've done, I've made two cuts like this. All right. So let us check it again. Is it acceptable or not? So to check that, again, I'll have to export it. This is the whole model. Okay. I just want to tell you that, yes, everything is included in this. Okay. Now, after making these two cuts, I'm going to export the whole model as we did before. Export. Yes. And I'm going to open the model in Abaqus. So this is the model that we had made in Hypermesh. Now we are going to solve it here, or we are going to run it here. And before running it, let me tell you that the optimized thickness of the material was 2.5, right? We need to use it here because already we have done thickness optimization. So we need to use the value of 2.5 mm. Now I'm going to run it here, submit. So it is completed. I'm going to visualize it. So again, as you can see, the maximum von Mises stresses are coming around 38 megapascals, which are lesser than 40 megapascals. So this slot is not creating any problems. Okay, this is acceptable, and this is the optimized design. So a design optimization or design finalization happens in a CAE environment, as I have shown you. If someone is telling that whatever you can design in a CAD package or software, that is design, that is entirely wrong. Okay, this is how you validate a design. This is how you optimize a design. Okay, and there are lots of projects that keep on coming in industries for design optimization. This is the process for that. I hope you learned from it, and I'll see you in the course. Thank you very much.